Today we will cover the topic stability analysis. So today we will discuss stability analysis. So first we will try to know the definition of stable system. What is the definition of stable system? Definition of stable system. A dynamic system is said to be stable when for all bounded inputs the dynamic system provides bounded outputs. A dynamic system is said to be stable system a dynamic system is said to be stable when for all bounded inputs the dynamic system produces bounded outputs. Fine, this is the definition of stable system. See, here two new terms are involved in this definition. One is bounded input, another one is bounded output. These are quite new. So next you will know what is bounded input. Bounded input is an input that remains within an upper limit and a lower limit. Bounded input is an input that remains within an upper limit and a lower limit. Similarly, we can define the bounded output. Bounded output is an output that remains within an upper limit and a lower limit. If we produce a plot between time t versus input u, then it looks like this. See, u is the input, so it has upper limit that we can denote by, suppose, u max, and it has the lower limit, I mean the lower value, that is say u min. Fine. Now, the input variable always remains within this upper limit and lower limit. It should not exceed the upper as well as lower limit. That is why it is called bounded input. Can you give one example of bounded input? Sinusoidal. Sinusoidal input is 1 bounded input. Step input is another bounded input. What about ramp input? Ramp input is not a bounded input. Now, just opposite of this bounded, that is unbounded. Fine. Unbounded. There is no existence of the term unbounded in reality because of the physical limitation of all instruments and equipments. There is no existence of the term unbounded in reality. It only exists in theory. Fine. Because of the physical limitation of all instruments and equipments. Now, so far we have discussed a little about the stability of open loop system. We have determined the roots of the denominator of a transfer function, and we discussed about the position of those roots in the complex plane, based on which we can comment on stability of open loop system. That we have discussed so far. Now, we will discuss the stability of closed loop system. So, before discussing, we need to know few important points. We derived the closed loop transfer function in generalized form. The closed loop transfer function we can represent by this expression: y bar is equal to GC GP ZF divided by 1 plus GC GP ZF ZM y set point bar plus ZD divided by 1 plus GC GP ZF ZM d bar. This is the general form of the closed loop transfer function. Fine. Now, the denominator of this transfer function we can write as 1 plus GC GP GF ZM. If we write this equals 0, then that is called the characteristics equation. This is the characteristics equation of the closed loop transfer function. Characteristic equation of the closed loop transfer function. For stability analysis, we will use this equation. Fine. This is the characteristics equation of the closed loop transfer function. This equation can also be write in this form: 1 plus open loop transfer function Z suffix OL, open loop, which is equal to 0. The characteristics equation we can also write by this form: 1 plus the transfer function of open loop equals 0. Now, we will write the definition of stable closed loop system. We will write the definition of stable closed loop system. A feedback control system is stable when all the roots of this characteristics equation lie in the left side of complex plane. A feedback control system is stable. A feedback control system is stable when all the roots of its characteristics equation have negative real part, negative real parts. Fine. A feedback control system is said to be stable if all the roots of the characteristics equation lie in the left side of the complex plane. So, if this is real axis and this is imaginary axis, all the roots should lie in the left side. This is the left side. Then we can say that the feedback control system stable. Fine. Now, we will just discuss different situations. So, first we will consider the type of roots, then what will be the corresponding root location in complex plane. And we will know the corresponding closed loop response, for a step change in set point SP. SP means set point. Fine. Suppose a characteristics equation has a number of roots. Among them, say a characteristics equation has a number of roots and the roots lie in the left side of the imaginary axis. That means all the roots have negative real parts, negative real root, not parts, negative real root. So, this is the complex plane, this is real axis and this is imaginary axis. Fine. So, suppose we are considering a single negative real root is there. So, the position of that should be here. What it indicates? The feedback system is stable or unstable? This is stable. So, if the characteristics equation has negative real root, then the system is stable. What will be the transient response, time t versus y? It will be like this. Definitely again step change in set point value. The transient response will be like this. Fine. It was the earlier state, I mean the process was at this position. Now we are going to introduce a step change in set point. That is why the process is going towards achieving a new steady state. In the second situation, we will consider among the roots one has positive real part. So, among the root one is positive real root. Now, we need to locate that root in the complex plane. This will be the location, positive real root. So, this is stable or unstable? This is unstable. Since the root has positive real part, so the feedback control system is unstable. What will be the corresponding transient response? This is time versus y plot. So, it will respond like this. Fine, it is going to unstable zone. In the third situation, we will consider complex conjugate roots. Complex conjugate roots with negative real part. With negative real parts. Now, if we will locate the roots in the complex plane, these are the two roots which are complex conjugate with negative real parts. Now, what about the stability? Stable, because the real parts are negative. So, the feedback control system is stable. What will be the transient response? T versus y. It will reach a new steady state with decreasing oscillation with decreasing amplitude. Fine. And in the fourth situation, we will consider complex conjugate roots with positive real parts. Complex conjugate roots with positive real parts. So, if we locate the roots in the complex plane, it looks like this. These are two roots, complex conjugate roots, which have positive real parts. So, what about the stability? Unstable. The closed loop system is unstable when it has two complex conjugate roots with positive real parts. And what will be the corresponding transient behavior? Oscillation with growing amplitude, like this. Fine. So, these are the four different situations created in a closed loop system. Now, we will note down few important points now. We will note down few important points on stability. Roots, axis, response. Real roots near the imaginary axis. Real roots near the imaginary axis result in slow response. This is the first important point. Real roots near the imaginary axis result in slow response. If we compare in the complex plane, it looks like this. One root is this one, another root is this one. So, the root which is near to the imaginary axis, that will provide slower response. Fine. Real roots near the imaginary or vertical axis result in slower response. If we consider two roots, so this is near to the imaginary axis, so it will provide slower response compared to another root. Complex roots near the imaginary axis result in slow response. Complex roots near the imaginary axis result in slow response. Suppose this is one set, this is another set. So this is near to the imaginary axis, so this set will provide slower response. Fine. Among these two complex conjugate roots, this one is near to the imaginary axis. So this the closed loop system having these roots will show slower response. Another important point is when the complex roots are away from the real axis. The complex roots away from the real axis, the more oscillatory the transient response will be. When the complex roots are away from the real axis, the more oscillatory the transient response will be. Say this is one set and another one is this one. Fine. So this set is away from the real axis, so this set will provide more oscillatory response. Fine. So these are three important points on the transient response, speed of the transient response, you can say. Fine. Now in the next we will discuss the one very popular stability analysis technique, that is Routh Array test. We will discuss in the next one very popular stability analysis technique, that is Routh Array test. Fine. This is purely an algebraic test. Routh Array test is purely an algebraic test. By performing this test, we can know how many roots have positive real roots, how many roots have positive real parts. By performing this test, we can know how many roots have positive real parts, how many roots have positive real parts. It is interesting that without determining the values of the roots, we can say how many roots have positive real parts by performing this test. There is no need to determine the roots. Just by performing this test, we can say how many roots have positive real parts. And another point is there is no need of any production of plot. Fine. There is no need to produce any plot for this particular case. And this method, this test is applicable when the characteristics equation is expressed in polynomial form. It is applicable when the characteristics equation is in polynomial form. This Routh test is applicable when the characteristics equation is in polynomial form. You can say this is the limitation of this Routh test. We discussed the characteristics equation that it has this form. I mean, we can express this as 1 plus GC GP GF GM equals 0. Now, suppose the process is a first order plus date time process. Suppose the transfer function of the process has this form: GP equals Kp exponential of minus tau ds divided by tau ps plus 1. Fine. The process is the first order plus date time system. Now, if we substitute Gp in this characteristics equation, we do not get polynomial form. So, what we can do in this case? In this case, we can go for approximation, maybe per day approximation, maybe Taylor series expansion. Remember, in that case, we can do only the approximate stability analysis. If we approximate this exponential term, say by per day approximation, in that case exact stability analysis is not possible, only approximate stability analysis is possible. Fine. Now, we will know the algorithm, I mean the test procedure. We will know the test procedure. What are the steps we need to follow to perform this Routh stability analysis? First point is we need to develop the closed loop transfer function. So, in the first, we need to develop the closed loop transfer function. Fine, this is the first point. Secondly, write the characteristics equation in a standard polynomial form. Write the characteristics equation in standard polynomial form. That is 1 plus Gc Gp Gf Gm equals 0. Now, we will write this in standard polynomial form as a naught s to the power n plus a1 s to the power n minus 1 a n minus 1 s plus a n equals 0. We need to represent the characteristics equation in this standard polynomial form, which is nth order polynomial. Let a naught be positive. Under this second point, few important issues we need to include. First point is, let a naught be positive. If a naught is negative, multiply both sides of this polynomial by minus 1. Let a naught be positive. If a naught is negative, multiply both sides of the polynomial by minus 1. So, if a naught is negative, then multiply both sides of the polynomial by minus 1. Fine. Now, inspect the coefficients. In the next, inspect the coefficients. A1, A naught, A1 up to an. Fine. Inspect the coefficients. If any one coefficient is negative, then the closed loop system is unstable. There is no need of any further analysis. If any one coefficient is negative, the closed loop system is unstable. No further analysis is needed. If any one coefficient is negative, the closed loop system is unstable. No further analysis is needed. If all the coefficients are positive, the system may be stable or unstable. If all the coefficients are positive, it is difficult to say whether the system is stable or unstable. So, we can say that if all the coefficients are positive, it may be stable, may be unstable. So, in this situation, we need to go for further analysis. Fine. So, this is the second point. A naught should be positive. We need to assume a naught be positive. If that is not positive, we need to multiply both sides of the characteristics equation by minus 1. In the next step, we need to inspect the coefficients. If any one coefficient is negative, the system is unstable. So, there is no need of further analysis. If all the coefficients are positive, the system may be stable or may not be stable. So, to conclude whether the system is stable or unstable, we need to go for further analysis. So, that is basically the third point, third step of this test. In the third step, we need to form Routh array. In the third step, we need to form Routh array. Fine. The Routh array consists of a number of rows. So, we will write the row one by one. This is first row, second row, third, fourth, like this, n plus 1. So, you remember, if the polynomial is nth order, the number of rows should be n plus 1. Fine. So, number of rows is equal to n plus 1, where n is the order of the polynomial. Now, we will write in this array all the coefficients of the standard polynomial. You just revisit the characteristics equation. The characteristics equation we have written in this standard polynomial form, which includes the coefficients starting from a1 to an. Now, we will write the coefficients like this. In the first row, we will write a0. In the second row, we will write a1. Then again a2, a3, a4, a5, a6, a7, like this. Last one will be a minus 1, an minus 1, and this one will be an. So, the elements of the first row include a1, a2, a4, a6, an minus 1. The second row includes a1, a3, a5, a7 to an. So, this is the way we need to write all the coefficients in first row and second row. The elements of the other rows we need to calculate. Fine. The elements of the other rows starting from 3 to n plus 1 we need to calculate. That calculation procedure has been proposed by Routh. Suppose the elements are a1, capital A1, capital A2, capital A3, like this. The elements of the fourth row are assumed B1, B2, B3, and the elements of the last row, n plus 1 row, are Z1, Z2, Z3. Fine. This is the Routh array. Now, how we can, I mean, what are the expressions for calculating the elements starting from third to n plus 1 row? Capital A1, which is the first element of third row, is calculated as A0, they are calculated as A1, A2 minus A0, A3 divided by A1, A1, A2 divided by minus A1 minus A0, A3 divided by A1. This is the expression for A1. The expression of capital A1 is A1, A2 minus A0, A3 divided by A1. The expression for capital A2 is A1, A4 minus A0, A5 divided by A1. I think now you can write the expression for all other elements. Expression for A2, you just left that column within which A2 is present. So, A1 A4 minus A0 A5 divided by A1. Similarly, the expression for A3 is A1 A6 minus A0 A7 divided by A1. A3 is present in the third column. So, you left the elements of third column and you start from first column always. That is why A3 has the expression, and that is expressed by A1 A6 minus A0 A7 divided by A1. What will be the expression for B1 then? B1 will be capital A1 small a3 minus small a1 capital A2 divided by capital A1. The expression for B1 we can write as capital A1 A3 minus small a1 capital A2 divided by capital A1. Similarly, we can write B2 equals A1 A5 minus A1 capital A3 divided by capital A1. Capital B2 we can write as capital A1 small a5 minus small a1 capital A3 divided by capital A1. Another element is B3. So, B3 we can write as capital A1 capital small a7 minus small a1 capital A4 divided by capital A1 B3. So, we need to write here the element A4. So, capital A1 small a7 minus small a1 capital A4 divided by capital A1, that is the expression for B3. So, this is the third point in which we have discussed the formation of Routh array. Next, we will analyze the stability in the fourth point. In the fourth point, we will discuss the analysis of this Routh array. So, what are the elements? Elements are A0, A1, capital A1, capital B1, last element is Z1. These are the elements in the first column. These are the elements in the first column. Now, the closed loop system is stable if all the elements are positive and non-zero. The closed loop system is stable if all the elements of the first column are positive and non-zero. The closed loop system is stable when all the elements of the first column are positive and non-zero. All the elements of the first column are positive and non-zero. Fine. So, this is one point. Another point is, if any one element in the first column is negative, then at least one root has the positive real part. If any one element in the first column is negative, then at least one root has positive real part. Another point is, if one element in the first column is negative, then at least one root has positive real part. I mean that root lie in the right half plane. See, we are mentioning here at least. That means there may be more than one roots lie in the right half plane. Now, question is, how we can say more than one root, or at what situation more than one roots lie in the right half plane? So, based on that, there is one point. Number of roots lie in the right half plane equal to the number of sign changes in the first column. So, in the next point we will write the number of right half plane roots is equal to number of sign changes in the first column. Fine. Suppose this is the first column which includes the elements A0, A1, capital A1, capital B1 to Z1. Among these elements, one is negative. That means, say this capital A1 is negative. So, how many sign changes are involved? 2. One sign change from second column to third column, another sign change from third column to third row to fourth row. So, 2 sign changes are involved. That means 2 roots have positive real parts. Fine. Suppose among these elements in the first column, one element is 0, then what about the stability? Among these elements in the first column, one is 0. Then what about the stability of that closed loop system? See, if all the roots are positive, then the system is stable. If even one root is negative, system is unstable. So, if one element is 0, that is the critical stability condition. So, at critical stability condition, we get sustained oscillation. So, if one element in the first column is 0, then we get sustained oscillation. I mean oscillation with constant amplitude. Fine. This is all about the Routh Array stability test, and one point is very clear that according to this Routh Array test, we can only know whether the closed loop system is stable or unstable. Using this test, we cannot determine the values of tuning parameters. Fine. See, we need to conduct the Routh stability test to know the stability of a closed loop system. That means the process including the controller. We want to know the stability of a closed loop system. Closed loop system means the process which includes the controller. Now, according to this test, we can only say that the overall system is stable or unstable. Using or conducting this test, we never determine the exact values of the tuning parameters. So, this is not basically the tuning test, this is basically a stability test. Thank you.